Hello my dear, good evening all. Greetings from ACE Engineering Academy and ACE Online. Welcome to three-day marathon session on AP GENCO TRANSCO DISCOM AEE for Electrical Engineering. Today's session we are going to discuss the important questions from power electronics. Myself Rajendra Gharse, Power Electronics faculty at ACE Engineering Academy, Hyderabad, right? So we're having a 1 hour session. We'll try to cover maximum possible questions, okay? Right. I have taken these questions from some previous year examinations and some GATE examination 1 mark questions also I have included. Even engineering services examination also few questions I have added, okay? So you can expect these type of questions in your upcoming examination, right? So start with the first question. The equivalent capacitance of a depletion layer with a dV by dt of 150 volt per microsecond, the capacitive current of a reverse biased junction of an SCR is 30 picofarad flowing through the junction is. Here they are asking what is the value of current. It is given that dV by dt is 150 volt per microsecond and capacitor value is also given 30 picofarad. We know when SCR is in an off state, we will be having a depletion layer present across the junction, and if the depletion layer is present means your junction is behaving like a capacitor, right? We know in case of capacitor we are having an expression I equal to C into dV by dt. Yes, no? I equal to C into dV by dt. Now here capacitor value given, it is equal to 30 picofarad, 30 into 10 to the power minus 12 into dV by dt. It is a 150 upon 10 to the power minus 6. So simplify this, you will get the value of the current, right? So if you see, you will be getting it as like 4.5 milliampere, right? Even you can post your answers in a chat box, okay, right? Yes, simple question, simply use I equal to C into dV by dt, all right? Yes. Next, this is a theory question. It is related to the GTO. GTO is nothing but gate turn off. We know GTO is a thyristor family device, but the difference between SCR and GTO is my GTO is a fully controlled device, SCR is a semi-controlled device, alright. By circulating the positive gate current, we can turn on the GTO, and by circulating the negative gate current, we can turn off the GTO, alright. So check this given statements. A GTO requires a special turn off circuit like the commutation circuit of a thyristor, that is a SCR. Definitely in SCR, commutation circuit is required to turn off. But in GTO, as I said, I can turn off the GTO by circulating the negative gate current. So statement 1 is not correct, right? Second, can be turned off by removing the gate pulse. No. To turn off GTO, we require the negative gate current, alright? Can be turned off by giving a negative pulse to the gate. Yes. So option C is the suitable option. And what about the D? Can be turned off by giving a positive gate pulse to the gate. No. To turn on the SCR, to turn on the SCR, we require the positive gate current, but to turn off we require the negative gate current, right? So correct option is option C. Very nice, right? Let us move forward. Next question. Yes. So this question is related to the voltage blocking, that is a series connection of SCRs. 10 thyristors are used in a string to withstand a DC voltage of 15 kilovolt. The worst case steady state voltage across the thyristor is 1800 volt, and the derating factor they are asking. So in SCR, we are having the series connection of SCR and a parallel connection of SCR. This question is associated with the series connection, alright? And we know in series connection as well as in parallel connection, we are having the two performance parameters, right? One is the string efficiency, second is the derating factor, alright? Come on, you can post your answers in the chat box. First, let us find a percent string efficiency. Percent string efficiency. Yes, it is equal to string voltage rating, that is a V string, upon number of SCRs connected in a series, number of SCRs connected in series into voltage rating of SCR, right, or available SCR, voltage rating of SCRs, right. This will give me the string efficiency, that will be into 100 I need to do, because the percentage that is should be into 100, right. So now what is the string voltage rating? String voltage rating is 15 kilovolt upon number of SCRs connected, they are saying it as a 10. So upon 10 into voltage rating of SCR is 1800 into 100, right. Yeah, check this, you will get the percent string efficiency, and from that we can get the derating factor. Yes, what is derating factor? Derating factor equal to 1 minus string efficiency, alright, 1 minus string efficiency. Yes, so if you see here, yes, yes, 83.33, that is a percent na string efficiency. So it is 1 minus 0.833. So if you see, it will be equal to 0. Yes, I think it is 15%, right, approximately 15.5%, correct hai? Correct, 15-16 approximately, right. So option B is the more suitable option, right. Yeah, so nearby, again it depends ki how many decimal points you are taking, that's it, okay, right. So check the options, from that you can say, we can say that it is this, yeah. So important is derating factor is 1 minus string efficiency, and how to find the string efficiency, alright, yeah. Next, right. Yes, this is also theory question, yeah, I am expecting answer from you guys. The phenomena is present in thyristors but absent in BJT, MOSFET and IGBT. Come on. And they have given the options like forward conduction, latching, forward blocking and reverse breakdown. Come on. Which of these phenomena is present in only thyristor family devices but it is absent in a BJT, MOSFET, IGBT? Means these are your transistor family devices. All these three are transistor family devices. So out of these four, which phenomena is absent in a transistor family devices? Yes, you can post your answers. Yeah, very nice, very nice. Yeah, correct. Yeah. So please check. All my thyristor family devices are latching devices like SCR, GTO, TRIAC. All these are latching devices. Latching means, for example, suppose SCR. I can turn on the SCR by using the gate current, but once my SCR turns on, after that if I remove the gate current, my SCR will not turn off. The meaning is my SCR has latched into on state, right. The thyristor family devices are latching devices, transistor family devices are non-latching devices. Check your BJT, MOSFET or IGBT, these are fully controlled devices. For BJT, if I circulate the base current, my BJT will turn on. But if I remove the base current, my BJT will come back to the off state. So BJT is not latching into on state, right? So important here, all the thyristor family devices are latching devices. All thyristor family devices are latching devices. and transistor family devices are non-latching. Transistor family devices are non-latching devices. Right? So which phenomena is absent in these transistor family devices? That is the latching. Right? So correct answer is option B. All right. Next question. Yeah. The main reason for connecting a pulse transformer at the output stage of a thyristor triggering circuit. Yeah. During our sessions also we discussed in power electronic circuits for power semiconductor devices we are using a pulse transformer, and generally the pulse transformer is connected at a control circuit side. What is the function of pulse transformer? Yes, come on, you can post your answers. Pulse transformer is used for we know pulse transformer is having a turns ratio 1:1. It is used for to provide the isolation between the control circuit and a load circuit, right? So pulse transformer is used to provide the electrical isolation between your control circuit and a load circuit. Check your SCR. We know SCR is a 3-terminal device, anode, cathode and gate. The circuit which is connected in anode and cathode of SCR is known as a load circuit. Generally your load circuit is having a high voltage, high current value. But the circuit which is connected between gate and cathode, that is known as a control circuit. My control circuit value of the voltage and current is comparatively low. So to provide the isolation between these two circuits, we are using a pulse transformer. Alright. So pulse transformer, answer should be the option C. Alright, option C. Yes, next. Yeah, in a commutation circuit employed to turn off an SCR, satisfactory turn off is obtained when? Yeah, come on. And they have given the option: circuit time constant is less than device turn off time, circuit turn off time is less than device turn off time, greater than, and again circuit time constant greater than device turn off time. Yeah, you can post your answers. Yes, for successful commutation of SCR, we know TC should be greater than or equal to TQ. Yes, no? TC is nothing but circuit turn off time and TQ is a device turn off time. So for successful commutation, TC should be greater than or equal to TQ. TQ is the device turn off time. Manufacturer of the device will specify the value of the TQ, right? That indicates how much time your device will take to turn off, and TC is a circuit turn off time. It is a time during which reverse voltage is maintained across your SCR by using commutation circuit. That time is known as a circuit turn off time. We know while turning off of a SCR, that is a minority charge carrier devices, when we are going to turn off these devices, first we are going to remove the stored charge carriers. Alright, and for removal of the stored charge carriers, we are maintaining the reverse voltage. Alright, so that time for which the reverse voltage is maintained, that time is nothing but TC. So minimum value of TC should be equal to TQ, but for successful commutation, TC should be greater than or equal to TQ. TC should not be less than. Yeah, so circuit turn off time should be greater than device turn off time. Option C is the correct option. Alright, yeah. Next. Come on. Next question. A 100-volt DC source with an RL load has a current of 20 milliampere at 100 microsecond. Yeah, they are saying at a 100 microsecond time, my current in a circuit is a 20 milliampere. Okay, it is means they are saying that DC voltage source we are having and it is connected with a RL load, right? DC voltage source and RL load, and it is given that the current in a circuit will reach to 20 milliampere value when the time is 100 microsecond. If a thyristor having a latching current of 30 milliampere, is connected in series between source and load and fired with a pulse width of 50 microsecond. Now pulse width of gate signal, that is they are saying TP, is equal to 50 microsecond. 50 microsecond. What is the current in the circuit? Come on, can anyone? It is given that a DC voltage source RL branch is present, and in the RL branch my current will reach to 20 milliampere when time is 100 microsecond, right? And they are saying if a thyristor is connected between, means you are having the circuit like this, DC voltage source, thyristor and RL branch. Yes, this is like 100 volt and this is R and L. Current here is I. My SR is having a latching current is equal to 30 milliampere. 30 milliampere. And we are maintaining the gate signal only up to 50 microsecond. So if I remove the gate signal, what will the current in a SCR, current in a circuit they are asking? Come on. Yeah, I have not yet received any correct answer. Can anyone? Please listen here. One thing is, in order to maintain SCR, even after removal of the gate signal, I need to maintain the gate signal till up to how much current? Latching current, right? I am repeating, please listen. If I want to maintain my SCR into on state even after removal of the gate signal, then at the instant of removal of the gate signal, my current from the SCR should be equal to which value? Latching current value. Now I am removing the gate signal at how much time? 50 microsecond. At 50 microsecond I am removing the time. Tell me, at 100 microsecond, if my circuit current is 20 milliampere, right, then at 50 microsecond my circuit current will be less than 20 milli or it is a greater than 20 milli? Come on. At 100 microsecond, if my circuit current is 20 milliampere, then at time 50 microsecond, my circuit current will be less than 20 milliampere or greater than 20 milliampere? Obviously it will be less than 20 milliampere. The meaning is when you are removing the gate signal, at that instant my SCR current value is less than this value. Means this value is less than your SCR latching current. Latching current is 30 milliampere, right? Means here we are removing the gate signal of a SCR before my SCR current reaching to 30 milliampere, that is the latching current value. So tell me whether my SCR will be maintained into on state or whether it will come back to off state. Come on. Yeah, don't take that 10 milliampere. It is, don't say proportional. Sir, for 100 microsecond it is 20 milliampere. So for 50 microsecond it will be 10 milliampere. No, it is not actually directly linear. But we know na DC voltage source across RL branch. My current in a circuit is, if you see, it is like this. Final value will come as like Vs by R. Vs by R, right? Now they are saying that when time is 100 microsecond, then current in a circuit is how much they are saying? It is a 20 milliampere, right? 20 milliampere. And I am removing the gate signal of the SCR. I am removing the gate signal of SCR at what time? 50 microsecond, means here I am removing the gate signal. So tell me, corresponding to 50 microsecond, my current in a circuit will be whether it is less than IL or greater than IL. It is less than 20 milliampere, means definitely it will be less than latching current value. Means before my SCR current reaches the latching current value, I am removing the gate signal of my SCR. So whether my SCR will continue operating into on state? No. SCR will come back to off state. If SCR will come back to off state means my circuit current will become 0. So answer should be the option D. Yes or no? Alright, please understand this question. Right. They are saying at 100 microsecond current is 20 milliampere. So definitely at 50 microsecond your current will be less than 20 milliampere. Less than 20 means definitely it will be less than latching current value. So therefore my SCR will not be maintained into on state, it will come back to the off state. Alright, chalo, next. Yeah, again this is a theory question, a simple question, come on. du by dt protection is provided to the SCR by, yes, please post your answers. We know that du by dt protection is required to avoid the false triggering of SCR, and for that we are using which circuit? RC snubber circuit na. So connecting a capacitor and resistor in parallel with a device. Alright, we are connecting a capacitor and resistor in parallel with a device, that is option C is the correct option. RC snubber circuit we are using. Alright, yes. Inductor is for di by dt, not for du by dt, be careful, okay? Yes, so don't say option B. Yes, it is C only, correct, right. Next, forced commutation necessary in dash dash circuits. In which circuit we require the forced commutation? Inverter grade SCR, MOSFET based circuits, converter grade SCR or GTO based circuit. Please listen. In the forced commutation, first thing is we are having a inverter grade SCRs and a converter grade SCRs. Converter grade SCRs means SCRs those are used in rectifier circuits. Inverter grade SCRs means SCRs those are used in inverter circuit. Now tell me, in rectifier circuit input is a AC. If input is AC, to turn off the SCR, whether we require the forced commutation? No, right? There the natural commutation is used. So converter grade SCR, which commutation used? Natural commutation. So forced is not required here. Natural commutation. Right. But in inverter grade SCRs, in inverter circuit, if I use the SCR, in inverter input is a DC. If input is DC, to turn off the SCR, we require the additional circuitry known as a commutation circuitry, right? So here the commutation circuit is required, means so we need to go for forced commutation. In forced commutation, to turn off the SCR, additional circuit is required, right? What are the MOSFET and GTO? MOSFET, GTO, these are fully controlled devices. So their control circuit itself is sufficient to turn on and turn off the device. Here commutation circuit is not required, simply control circuit is sufficient to turn on and turn off the device. Okay, so these are fully controlled. Fully controlled. And this is also fully controlled. Right, so correct answer is option A. In inverter grade SCRs we require the forced commutation, right. Next, in which of the following both frequency and voltage can be controlled? Controlled means variable voltage, variable frequency output. It is a inverter, cycloconverter and AC voltage controller, cycloconverter and AC voltage controller, inverter and cycloconverter and inverter and AC voltage controller. Yes. We know inverter converts DC to AC, and my inverter will give me the output in form of variable voltage and variable frequency. Cycloconverter also give the output in form of variable voltage, variable frequency. So cycloconverter and inverter, these two will give the output in form of variable voltage, variable frequency. What about AC voltage controller? AC voltage controller will give output only in form of variable voltage but constant frequency. Okay, right. Same. So here suitable answer is inverter and cycloconverter. Right. Next. Yeah. When the firing angle alpha, it should be alpha. When the firing angle alpha, consider it as alpha, of a single phase fully controlled rectifier feeding constant DC current, that is highly inductive load, into a load is 30 degree, the displacement power factor. Single phase full converter, single phase full converter load is highly inductive, firing angle alpha is 30 degree, and they are asking a displacement power factor, that is DPF. Yes, for highly inductive load, how to find the input power factor? By using DF and DPF, alright? Yeah. So check, we have written the expressions for single phase full converters. What is the DPF? It is a cos alpha. So it is equal to cos of alpha is a 30 degree, correct? So cos alpha, that is cos 30 degree, you will be getting it as equal to root 3 by 2, correct? Root 3 by 2, yes. Yes, so option D is the correct option. Yeah. Yeah, this type of question they have asked, right? Next. A three-phase fully controlled converter, that is a three-phase full converter where the 6 SCRs are used in a bridge configuration, is feeding a power into a DC load at a constant current of 150 ampere. Load current is constant, that is load is again highly inductive. The RMS current through each thyristor of the converter, they are asking what is the IT RMS. IT RMS. Now for three-phase full converter, we are having 6 thyristors. 3 are in upper group, remaining 3 are in lower group, right? T1, T3, T5, T4, T6, T2. We know at any instant of time how many SCRs conduct? 2 SCRs. One from upper group, second from lower group. And each SCR conduct for how much angle? Each SCR conduct for 120 degree angle, right? So if you see my IT waveform, even during our sessions we have drawn this waveform. This is omega t 0, let me draw here IT1. We have drawn IT1 waveform, it is like pi by 3 plus alpha till pi plus alpha out of 2 pi. When thyristor is in a on state, through thyristor which current flows? Load current, right? And for this waveform we know IT RMS equal to amplitude square, function duration is 2 pi by 3 and periodicity is 2 pi to the power 1 by 2, okay? So it is equal to I0 by root 3, that is equal to 150 upon root 3, right? 150 upon root 3 ampere, right? Yeah. Each SCR conduct for only 120 degree, okay, right? Yes, thyristor current they are asking, right? So the correct answer is option D. Yes, option D is the correct answer, right? Not C, it is D, 150 by root 3, okay, right? Next. In a 2-pulse bridge converter with freewheeling diode, 2 pulse means full wave rectifier, single phase full wave. The width of the diode current pulse over one cycle is, they are asking the diode current pulse width over one cycle of supply. Can anyone? Single phase full converter, freewheeling diode present means load is a REL load with the freewheeling diode. Tell me, in one cycle of supply, my freewheeling diode conduct for how much angle? Recall your circuit operation, right? Circuit diagram and operation. Check, my freewheeling diode will conduct during 0 to alpha, pi to pi plus alpha, 2 pi to 2 pi plus alpha, 3 pi to 3 pi plus alpha, and so on. Okay? So if I draw the freewheeling diode current waveform, it is like this. Alpha, this is pi to pi plus alpha, out of one cycle of supply is 2 pi. So in 0 to 2 pi, my freewheeling diode conduct during 0 to alpha and pi to pi plus alpha, right? So here they are asking the width of this freewheeling diode current corresponding to one cycle. One cycle is 0 to 2 pi. One cycle means one cycle of supply. In that my freewheeling diode conduct here and here na, so that width should be alpha plus alpha, that is 2 alpha. Answer should be 2 alpha, alright? Yes. Next, a 4-quadrant operation require 2 full converters connected in. Yeah, can anyone? 4-quadrant operation, for that which converter is used? Dual converter. And dual converter means it is the anti-parallel connection of 2 full converters, na? Or it is also known as back-to-back connection of 2 full converters. Okay? So here back-to-back connection. Yeah. In dual converter, two full converters. In dual converter, 2 full converters connected in a anti-parallel. Or back-to-back. Anti-parallel or back-to-back. And dual converter operate in which quadrants? 4 quadrants. Dual converter operate in all 4 quadrants. All 4 quadrants, right? Yeah. So 4-quadrant operation, and they are saying 2 full converters connected in. Yeah. So you need to think about the dual converter, and the dual converter is nothing but anti-parallel connection of 2 full converters. So your answer should be option C, right? Yeah, option C. One more converter we are having, that also operate in all 4 quadrants. That is a type E chopper. In DC to DC converter we are having the chopper, types of the choppers based on quadrants of operation. Your type E chopper also operate in all 4 quadrants. But this question is related to dual converter, okay? Because they are saying 2 full converters, means it is a dual converter again, right? Next. Yeah. The average load voltage across a resistive load of a single phase bridge converter connected with 2 SCRs and 2 diodes. Bridge converter, 2 thyristors, 2 diodes are used, means it is a semi converter, right? Semi converter, that is single phase semi converter, operating at any firing delay angle alpha and supplied at 200 volt 50 hertz is. Yeah, they are asking average output voltage, average load voltage means average output voltage, V0 average expression when the supply voltage is 200 volt RMS value. By default given voltage AC quantity is nothing but RMS value, okay? They are talking about the single phase semi converter. Single phase semi converter. In semi converter, what is the V0 average? In semi converters, no negative pulse in output voltage. Semi converters are having inherent freewheeling path, alright? Yeah, so expression will be Vm by pi into 1 plus cos alpha, na? 1 plus cos alpha. Now here Vm is a 200 into root 2. 200 root 2 upon pi into 1 plus cos alpha. Alright. So if you see the options, yes, root 2 into 200 by pi into 1 plus cos alpha. Option C is the correct option. Alright. Yeah, simple question. But you need to understand the question is related to semi converter. Right. Next. Yes, in a thyristerized converter, a freewheeling diode is used. Come on, you can post your answers. Simple theory question. First option is add to the conduction current of the thyristor, oppose the thyristor conduction, conduct current during the off period of the thyristor, protect the thyristor by providing a shunt path. Whether freewheeling diode is used to protect the thyristor? No. Come on, tell me most suitable option. Yes, to conduct the current during the off period of the thyristor, right? So in freewheeling diode or RL load with freewheeling diode, your freewheeling diode will conduct when my supply voltage is having a negative pulse, alright, and supply voltage will try to turn off your thyristor. So at that time your freewheeling diode will come in a picture, okay? So option C is the suitable answer, right? Next. A single phase full converter SCR bridge with a freewheeling diode, okay, no problem, is connected to RLE load as shown. Vs is equal to 230 root 2 sine of 314 volt. The average load current is 8 ampere is constant over the working range. The firing angle alpha delay is, they are asking alpha value. Yes. Now here single phase full converter, they are saying single phase full converter and with a freewheeling diode, means they are saying in this box we are having a single phase full converter and also freewheeling diode is connected across the load branch. Okay, right. And now tell me, first can we write V0 average by using this I0 they are saying constant 8 ampere, okay, and resistor, I want expression for V0 average in terms of load current, load resistor and EMF. Yes, can I write V0 average equal to I0 into R plus E, right? Because average voltage across inductor is 0. This indicates voltage, average voltage across resistor, and this is the average voltage across EMF. EMF is a constant, so its average value equal to simply E, right? Simply E. So now from this I can write I0 is a 8 into 0.5 plus E is a 120. E is a 120, right? So this is equal to 124. V0 average is equal to 124 volt. 124 volt. All right. Now, what is the expression for V0 average? What is the expression for V0 average for single phase full converter RL load with freewheeling diode? It is a Vm by pi into 1 plus cos alpha, na? 1 plus cos alpha. Yes, no. Now put V0 average is 124 is equal to Vm by pi. Vm is a 230 root 2 upon pi. Yes, Vm should be 230 into root 2, not divided by. Yes. Into 1 plus cos alpha. All right. Now from this we can get alpha, na? From this we can get alpha. All right. Yeah. Yes, you can check this. What you are getting? 53.2. Correct? Right. Don't use here expression of full converter directly. Important is full converter with the freewheeling diode. So be careful. Okay? Yeah. So it is Vm by pi into 1 plus cos alpha. All right. Chalo, next. Yes. Yeah. An AC voltage source of 120 sine of omega t is supplying power to a resistive load. Yeah, supply voltage given, load is resistive given 10 ohm. Yeah. Through a switch. So between supply voltage and load we are having a switch. Assume the switch is ideal and initially off, and it control works in such a way that it toggles every time when the source voltage crosses 0. The power absorbed by load is, in watts they are asking. Yeah. Come on, can anyone? Circuit is like this. Yeah, I am giving hint. It is supply voltage. Next, we are having a switch here. Yeah, let us take switch simple because they have not mentioned whether it is thyristor or anything. Okay, so I am taking it as switch means normal, like its symbol of switch, and here it is a resistive load. This is Vs, R, and our task is to find the load power. So for that, let us find V0. And switch toggles every time the supply voltage crosses 0. This is my switch. Yes, supply voltage is pure sinusoidal. All right. Pi, 2 pi 3 pi and so on. Tell me how will be my V0 waveform. Yes, switch toggles means what? It is given that the switch toggles every time when the source voltage crosses 0. Your source voltage is crossing 0 at these points na, here, here, here and here again. And now tell me, they are saying initially switch is in a off state. So before this point it is switch is in a off state. So when supply voltage is having a 0 crossing here, then at that time your switch will turn on. When switch turns on, what is my output voltage? Same as that of the supply voltage na, 0 to pi Vs positive. When switch is turned on, I am getting V0 equal to Vs. At pi again supply is having a 0 crossing. So therefore at pi my switch will again turn off. It toggle means it will again turn off, right? So when switch turns off here, then during this interval my switch will be in a off state. So therefore it is again 0. Again at this point my supply voltage is having a 0 crossing. My switch will again turn on there. When switch turns on, then output voltage is again same as that of supply voltage, right? So it is like switch has turned on here, switch has turned off here, again turned on, again switch here going to turn off, right? So can I say that this output voltage waveform is like your half wave uncontrolled rectifier, alright? Yeah. Now what is the V0 RMS for half sinusoidal signal? V0 RMS is equal to amplitude by 2, right? What is amplitude? It is peak value 120 upon 2, that is equal to 60. V0 RMS is equal to 60 volt, alright? So therefore can I write load power equal to V0 RMS square upon R. So you can check it as 60 square upon R. R is a 10. Yes, so it is equal to 360 watts. Fine, 360 watt. So answer is option A. Correct? So switch toggles means you should understand here. Okay? Right. So your switch is like your normal diode again. Right? My diode also toggles na. Here switch diode turns on, here turns off. Right. Next. Yeah. A single phase full wave midpoint SCR converter. Full wave midpoint. Okay. Uses a 230 volt / 200 volt transformer with a center tap on the secondary side. The PIV per SCR is peak inverse voltage rating of the SCR they are asking, and but here transformer turns ratio is not 1:2. It is 230 at primary, secondary side voltage is a 200. Yeah, can anyone? Your circuit is like this, midpoint rectifier, and here you are having the load. Yeah, okay, load they have not mentioned na. Yeah, no problem. So simply let me mark it as load. And here we are having the SCR T1, T2. Okay. Tell me what is the PIV rating. Suppose this is VT1 and VT2. If here voltage is 230, here I am getting supply voltage when positive, it is a 230. What I will be getting voltage at secondary side? 230 / 200 na. So secondary side voltage I will be getting it as a 100 here, and here it is again 100 na. Here it is again 100 volt. But this 230 volt is a RMS value, right? Now tell me, when thyristor T1 turns on, at that time what is the voltage that will be appearing across thyristor T2? When T1 turns on, check this positive terminal of VT2 is connected here, negative terminal of VT2 is connected at this side na. Means I can say that entire secondary winding voltage will appear as a reverse voltage for thyristor T2. But this 100 volt, this is a RMS value. What is the peak value? Total is 100 plus 100 is 200 volt, that is a RMS. So peak will be 200 into root 2. So my PIV should be PIV rating of SCR is equal to 200 into root 2 volt, right? 200 root 2. So your answer should be, yeah, 200 root 2 means it will come like 282. Okay, you can check it. All right, so 282. Yeah, no, don't think sir PIV by default it is 2 Vmax. That 2 Vmax is true only when your primary to secondary turns ratio is 1:2. If primary to secondary turns ratio is 1:2, then only you can say PIV equal to 2 Vmax. In general, PIV rating of SCR is nothing but peak value of voltage across your secondary winding. Peak value of voltage across the full secondary winding. All right? Yeah. Right. Clear? Here turns ratio is important, 230/200. Right. Turns ratio is not like 115/230. It is not 1:2 na? Next. A single phase diode bridge rectifier is required to supply a DC output voltage of 220 volt to a bulb of resistor 25 ohm. The average and RMS value of diode current. Diode bridge rectifier they are saying, diode bridge rectifier and load is a resistive. Diode bridge rectifier and load is resistive. How will be my diode current waveform? Check. They are asking about the average and RMS value of diode current. Diode D1, D2 conduct during which interval? 0 to pi. Pi to 2 pi it is off. 2 pi to 3 pi. Again D1, D2 conduct. Diode bridge rectifier means we are having the 4 diodes D1, D2, D3, D4 connected in a bridge configuration. My D1, D2 conduct only from 0 to pi. Pi to 2 pi D3, D4 conduct. At that time D1, D2 off. Okay. And now tell me, when diode D1, D2 conduct, which current flows through D1, D2? It is a load current only. It is equal to load current only. Right? So this is my load current. Load current peak value, let me mark it as Im. It is equal to Im. Now can we find ID average and ID RMS? It is a half sinusoidal. So average value equal to amplitude by pi. Amplitude is Im upon pi. How to write Im? Im is Vm by load resistor. Supply voltage peak value upon R upon pi. So Vm is the yes. So here it is given that single phase diode bridge rectifier is equal to supply DC output voltage, okay, of 220 volt. DC output voltage they have given, means here they are saying DC output voltage means V0 average is equal to 220 volt. Okay. Now DC output, how is your DC output voltage waveform? It is like this: 0, pi, 2 pi and 3 pi na? Pi, 2 pi and 3 pi. Bridge rectifier. What is the peak value of your output voltage? It is Vm. So can I write for this waveform my V0 average equal to 2 Vm by pi. You can see it is like 1 by pi integration 0 to pi Vm sin omega t. Okay. So it is 2 Vm by pi. Now it is 220 is equal to 2 Vm by pi. From this you can get Vm na? It is 220 into pi upon 2, that is equal to 110 into pi. This is Vm. Now you can put that Vm here. You will get your ID average. Here it is 110 into pi upon pi into R. R is 25. So it is pi cancel out, 110 upon 25. Okay. And what is the ID RMS? ID RMS equal to simply Im by 2, which is equal to Vm by R upon 2. Right. Vm is the same 110 pi upon 2 into 25. Yeah, you can check this. Right. what you are getting 4.39 and 6.91, correct है या different है? Tell this ratio 110 upon 25. Yes, it is 4.4. Yeah, this is 4.4. And what about this one? Yes, 6.91. Right, so option C is the correct option. All right, be careful, this 220 is, they are saying it is the output voltage of your rectifier. This is not supply voltage. Right. Next. Yes. If the constant output current of a 3-phase full converter is a 220√3 ampere, then peak and RMS current value of supply line current. Come on. Supply line current means IA waveform. They are not asking thyristor current. They are asking supply line current value for 3-phase full converter. If you recall 3-phase full converter, during our analysis we have drawn the IA waveform. Supply star connected. So line current, or you can say it as phase current, doesn't matter. Right. How is the waveform we have drawn? It is a cos square, 0 to alpha, pi by 3 plus alpha to pi plus alpha, 2 pi by 3 plus 4 pi by 3 plus alpha till 2 pi plus alpha. It is alpha pi by 3 plus alpha till pi plus alpha, here 4 pi by 3 plus alpha till 2 pi plus alpha. My waveform is like this, 0 to alpha it is negative, yes, this is like I0 and this is minus I0, right? During our analysis we have written IA RMS expression also. What is IA RMS? Is equal to under root 2 by 3 into I0, which is equal to under root 2 by 3. What is I0? 20√3. Root 3 cancel out. So it is equal to 20√2. This is RMS. Okay. And what is the peak value? Peak value of IA is same as that of your I0. Right. So IA peak is same. That is a 20√3. And RMS is 20√2. So 20√3 and 20√2. Option D is the correct option. Right. Yeah. Yes. We have drawn this waveform during our sessions, right? And we have written IA, RMS, etc. Yes, next. A single phase full converter bridge is connected to RLE load. The source has a RMS voltage of 230 volt and the average load current is a 10 ampere. Right? The firing angle for which the power flow from DC load to the AC source. They are asking at what alpha value your power flows from DC side to AC side. Means it is a inverter mode operation. Inverter mode operation. Check in inverter mode operation we have written required conditions. In that one of the necessary condition was firing angle alpha should be greater than 90 degree. Right? Alpha should be greater than 90. Here they are asking alpha value in radians. Tell me load current given 10 ampere and R, E and L value, that is load, resistor, inductor and EMF value given. In inverter mode operation, question is on inverter mode operation. Inverter mode operation. For inverter mode operation, how to write V0 average? For inverter mode operation, we are reversing the polarity of EMF. Okay, so it is a I0 into R minus E. For normal motoring mode, it is I0 into R plus E. But for inverter mode, we are reversing the polarity of EMF. So that's why it is a minus E. Now you can check here. I0 is a 10. Resistance value, yes, 0.4. minus E is a 120. Okay, so it is a 4 minus 120, that is minus 116 volt. This is V0 average. Which converter they are talking? Single phase full converter. Single phase full converter for inverter mode operation. What is the V0 average? 2 Vm by pi into cos alpha, that is equal to minus 116. So we can put value 2 into peak value of supply is 230 root 2 upon pi into cos alpha, that is equal to minus 116. Okay, simplify this, you will get alpha. Here alpha first you will get maybe in degree, after that you are required to convert that in a radian. Okay, right. You can check this calculation, that's it. Next, yes, yeah, a single phase full wave diode bridge rectifier is supplied from 200 volt 50 hertz source. Full wave diode bridge rectifier they are saying. The load is 100 ohm resistor. The peak inverse voltage of each diode in the rectifier is. For diode rectifier, what is the PIV? PIV rating of each diode is Vmax, na? In diode rectifier, it is a Vmax, which is equal to, Vmax is a RMS value 200. So peak value is a 200 into root 2 volt, right? 200 root 2. So answer should be option C, right? Next. A single phase diode bridge rectifier supplies a highly inductive load. The load current can be assumed to be ripple free. The AC supply side current waveform will be source current waveform they are asking. AC side current means source side current. Diode rectifier, load is highly inductive. What is the source current waveform? You can relate this with your thyristor rectifier. Difference between thyristor rectifier and diode rectifier is, in thyristor rectifier if I put alpha 0 degree, I will get diode rectifier. Tell me, in thyristor rectifier for highly inductive load, how is my supply current waveform? It is a square waveform, na? It is a square waveform, right? And if I put alpha 0 degree, I will be getting my supply current waveform is like this. 0 to pi, pi to 2 pi, and so on. Load current is a constant, but supply current we are getting it is a square function. This is for diode. For thyristor rectifier, how is the current waveform? Alpha, pi plus alpha, 2 pi plus alpha. This is like alpha, pi plus alpha, 2 pi plus alpha. This value is I0 and here it is minus I0, right? If I put alpha 0, this is for thyristor rectifier. For diode rectifier, simply put alpha 0. If I put alpha 0 means this waveform will be getting shifted to the left hand side, na? By how much angle? Alpha angle, right? If alpha 0, then you will be getting this waveform. This is for diode rectifier. So the nature of source current is a square waveform. Here also square. Thyristor rectifier also it is a square only. Alright. Next. Next. Yeah. A single phase semi converter is operated from 125 volt 50 hertz AC supply. Semi converter. 2 thyristors, 2 diodes. If the average output voltage is 25% of maximum possible average output voltage, the firing angle is, they are asking alpha value. Tell me, for semi converter, what is the output voltage expression? Vm by pi into 1 plus cos alpha, na? Vm by pi is into 1 plus cos alpha. Right. Now, at what value of alpha I am getting V0 average maximum? When alpha 0 degree. If alpha 0 degree, this term will become maximum, that is a 1, right? So at alpha equal to 0 degree, V0 average is the maximum. V0 average is a maximum. And now can I say that maximum V0 average is equal to, put alpha 0 here, it is 1 plus 1, that is 2 Vm by pi. Maximum value of V0 average is 2 Vm by pi. But now here our task is to find the alpha value if the average output voltage is 25% of maximum output voltage. Means they are asking if V0 average is equal to 25%, means 0.25 into maximum V0 average, then what is the alpha? And now how to simplify? V0 average expression is Vm by pi into 1 plus cos alpha. Vm by pi into 1 plus cos alpha. That should be equal to 0.25 into, what is maximum V0 average? 2 Vm by pi. So from this you can see, this will get cancelled out now. Pi cancel out, correct? So I can say that 1 plus cos alpha equal to 1 plus cos alpha equal to 0.5. So from this can I get alpha? Yes. Okay. So alpha will become 0.5 minus 1, that is minus 0.5, that is nothing but 120 degree. Right? 120 degree. Here please understand, if alpha 0 degree, then your maximum output voltage will be there. Okay, and for V0 average of 25% of maximum V0 average, what is alpha required? You are required to simplify like this. Okay, so answer should be 120 degree. 120 degree. Yeah, let us discuss few more questions. I think we already completed the time. Okay, anyways, let us discuss few questions. By considering the effect of a source impedance means source resistance plus source inductance. Okay, yeah. But majorly this question is associated to the source inductance effect. Yeah. In a single phase full converter, the output voltage will be maximum and minimum respectively for the overlap angles of. So at what overlap angle mu? Your output voltage will be maximum and your output voltage will be minimum, they are asking. Can anyone check your output voltage waveform when the source inductance is present? When source inductance is present in single phase full converter, your output voltage waveform is like this: alpha, alpha plus mu, pi, pi plus alpha plus mu, 2 pi. Check this waveform we already drawn during our analysis. This is alpha plus mu, pi plus alpha plus mu, and 2 pi, right? Now this indicates your mu, na? This is also mu. Alpha to alpha plus mu means this angle is mu. Pi plus alpha to pi plus alpha plus mu means this angle is again mu. So here tell me, during overlap angle mu your output voltage is 0. During overlap angle mu your output voltage is 0. Then tell me at what value of overlap angle mu I will be getting the output voltage minimum and output voltage maximum. Can I say that if mu value is 0, if mu is 0 means no zero interval. No zero interval means my output voltage will be maximum. If mu equal to 0, for 0 mu, for mu equal to 0, I am getting V0 average maximum, and that V0 average will be same as that of your output voltage waveform of single phase full converter without source inductance. If mu 0 means this zero interval will be getting absent, means you will be getting negative pulse, after that positive pulse, negative pulse, and again positive pulse. So in that case you will be getting the maximum output voltage. And if mu equal to 180, for mu equal to 180 degree, mu 180 means my firing angle, overlap angle mu will be present from this alpha to pi plus alpha. During this entire region my mu will be present. If mu is present means my output voltage will be 0 during this entire region, and same will be getting 0 after this point also. So your output voltage will be 0 when mu equal to 180 degree. It is a minimum, that is a 0. Here simple understand, during overlap angle mu my output voltage is a 0, right? If you want output voltage to be maximum, then my 0 value should be avoided in output voltage, and that is true when mu value is a 0. And if mu is maximum, that is 180, then output voltage will be minimum. So answer should be, yes, the output voltage will be maximum. Maximum is at 0 degree and minimum is at 180 degree. So answer is option C, right? Okay, chalo. Yeah, last 2-3 questions we'll discuss, okay, and then we'll stop. Yeah, a half wave thyristor converter supplies a pure inductive load. Chalo, half wave rectifier, pure inductive load they are saying. If the triggering angle is of thyristor is 100 degree, alpha is 100, then the conduction extinction angle will be beta. Single phase half wave controlled rectifier. Thyristor converter means controlled rectifier, and load is purely inductive. Tell me, in purely inductive load, what is the expression for beta? Recall, single phase half wave controlled rectifier, load is a purely inductive. My beta equal to 2 pi minus alpha, that is equal to 360 degree, minus alpha is 100, right? That is nothing but 260 degree. Yes, no? Beta value is 2 pi minus alpha. Alpha is given 100 degree, right? Yeah. So it is 260 degree. Answer is option A. Next, single phase full converter can operate in, single phase full converter operates in which quadrants? Yes, single phase full converter operates in which quadrants? First and fourth quadrant, right? That is nothing but first and fourth. Single phase full converter operate in first and fourth quadrant. First and fourth quadrant, right? First and fourth means it will give me the 2 quadrant operation, na? First and fourth, that is 2 quadrants. Dual converter operates in 4 quadrants, okay? Semi converter operates in first quadrant, okay, right? Okay, so friends, these are the few questions. Actually we are running out of time, okay? So if you want this PDF file, okay, you can send message after this video, okay, and I will try to upload this PDF file of these questions, okay, because few questions are there. Due to the absence of lack of time, we are unable to discuss these questions. Yeah, okay, right. Okay, we'll stop here. Thank you, thanks to all of you, and all the best for your examination.